Okay, so let's just go over these here, guys. All right, so have we seen that graph before? Was it the example we did yesterday? Yeah, see, sometimes I do that. All right, said I'd used it on an exam. I also used it on a quiz once. I just like that graph. Okay, it's a good graph. All right, what's going on in part A? Nothing. Well, it's not always a good idea to say nothing. We would say the object is stationary. Yeah, that would be a better way to describe that. Okay, the object is not moving. The object's position is not changing over the course of 1 second. Something like that. Make sure you have a good description of what it's doing. Okay, in part B, what's the object doing? Kennedy. Okay, so it's moving at a constant velocity in a positive direction, okay, because we can see that the position there is becoming more positive. It's going from positive 20 to positive 60, okay. What's going on in part C? Stationary, okay, and in part D? Okay, it's going backwards, it's reversing at a constant velocity. Okay, as soon as you give a direction, if you say reversing, going backwards, then you can't say constant speed anymore because you've given a direction. All right, so now you need to say it's at a constant velocity. You got to give the vector. Okay, and I would say that that's the most correct way to say that would be moving backwards at a constant velocity. Okay, reversing at a constant velocity. All right, so that's what we would have been looking at there. Okay, and then for part B, it said calculate the velocity in each section, or in section D. All right, so in section D, if I want to calculate the velocity in section D, there's two ways to do it, even though mathematically they're exactly the same thing. I could calculate the what of that line. I could calculate its slope, or mathematically identical to that, I could figure out its displacement in part D and divide that by the time, which would be the rise over the run anyway. Okay, so I would say probably easier in this case, since I don't have a b or or anything like that to use y equals mx plus b, to just do this. Velocity equals displacement over time. Its displacement is, it goes from 60 to 20. So its displacement is negative 40 meters. All right, if you recall yesterday we said that displacement is final position minus initial position. All right, that would mean 20 minus 60. Okay, that gives us a negative number. That indicates that it is going backwards. Okay, and that takes about 1.5 seconds. Okay, so 40 over, negative 40 over 1.5. It's going to give us negative 27 meters per second. Okay, or 26.7 if you want to put it to the decimal place. Okay, would you have to indicate the negative on that? Yes, because it asked for velocity. Okay, any questions on how number one would work? Daniel? That would also be fine. Yeah, I would say though you need to round the 0.6, because the next number is also a higher than 5, right? Okay, for question number 2. All right, we've got another position versus time graph, so there were no velocity versus time graphs on this particular quiz. Okay, calculate the average speed of the object over its entire trip. Oops, sorry. Average speed is total distance over total time. All right, so it goes 20 meters, then it doesn't go anywhere, and then it goes another 20. Okay, so I got 20 plus 20, and what does it do here? It goes 20. Okay, does it matter that it's backwards? Not for speed, it doesn't. All right, so the total distance is 60 meters. The total time, 12 seconds. I believe that comes out to 5 meters per second, does it not? Okay, there's our average speed over the whole trip. Okay, ringing a bell for everybody. All right, position versus time graphs tend to be the easier of the two. All right, it's velocity versus time graphs where people start to have difficulty, let's say. All right, okay, let's get to work on the booklet there that I gave yesterday with those graphs on it, because I think most of you are kind of getting through the position versus time ones, and we'll definitely get into the velocity versus time ones today, and we'll go over any trouble that we have with those. Okay, so yesterday, if you recall, okay, we talked about how we could calculate acceleration from these kinds of graphs. Okay, we said that acceleration is the rate of change of velocity. which means it's the change in velocity divided by time. In other words, the what of a line on this graph, the slope of a line on this graph. Okay, so the first part of this is asking us to calculate the acceleration between 12 and 14 seconds. So that would be here and here. Okay, now I've got a line there, but I don't have a y-intercept for it. I don't have any of that kind of stuff. Can I still do like a rise over run slope calculation? I can. Okay, and if I do that, that's going to be y2 minus y1 over x2 minus x1, which we said yesterday was really doing this. The final velocity minus the initial velocity, and what's the change in x? Time. Okay, that's how we calculate acceleration. That's your acceleration formula. And I'm going to photocopy your formula sheets here this morning and give them out to you as well. Okay, so my final velocity at time 14 seconds is negative 6 meters per second. And I'm going to subtract my initial velocity, which is 2, positive 2. And that takes 2 seconds. Everyone follow me there? Right? From between 12 and 14 seconds is 2 seconds. Okay? And at time 12 seconds, I'm moving at 2 meters per second. And at time 14 seconds, I'm moving at negative 6 meters per second. So I'm obviously accelerating which way? Backwards. Yeah, negatively. Okay? In a negative direction. All right. So when I do this, this is in meters per second, remember, and this is in seconds. Okay? So I'm going to have negative 8 divided by 2, which is going to be negative 4 meters per second squared, or meters per second, right? I would accept either one. If you wrote either one, they're both right. Okay, so if meters per second makes more sense to you, write it down, because it's also right. Okay, does that answer your question, Emily? Okay, all right, are we struggling with anything else on there? Okay, keep her going then. Okay, remember that when we're dealing with a velocity versus time graph, if we want to find the displacement of the object during any part of the graph, we're still using this formula. Okay, average velocity equals displacement over time. Okay, if I want to find displacement, I'd multiply average velocity by time, which we said is basically like calculating the area of all the shapes on the graph. Okay, so for example, if I'm calculating the displacement during this 3-second interval here, okay, I know that my time is 3 seconds, which is the base of my triangle, and I know that my average velocity is the height of my triangle divided by 2. Okay, because for half of this 3-second interval, I would be going slower than this value, and for half of this interval, I would be going faster. That makes the halfway point the average velocity. That's why we say that you can just calculate all the areas. When you do that, you're really just doing average velocity times time equals displacement. Okay, so you find it for each section, and then you can add them all up at the end. Only if it's a triangle, right? If it's like for this one here, I wouldn't, because it's a rectangle. That would be just base times height traveling at a constant velocity during that time. So the average velocity for this part is 2 meters per second. Everyone follow me there? Right? Because velocity doesn't change. The average velocity for that rectangle is 2 meters per second. Okay? But any time where the line goes downwards or upwards or is at a slant, then we know velocity is changing, and we need to use the average during that time. Okay? Okay, so number 8 has to do with that whole drawing the tangent thing that we talked about yesterday. Okay, remember I explained to you how I passed university calculus? Okay, and that the only thing I understood was that a curve is an infinitely large number of infinitely small straight lines. Okay, well, that's what we're doing here. Okay, if I want to find the instantaneous velocity at time 2 seconds, which is right here, okay, then I need to know what the slope of the line is, or the slope of the curve is at that point. Well, the curves at that point is the straight line that exists right there is way too small for me to calculate the slope. So I need to draw a tangent, because a tangent will be parallel and thus have the same slope as the curve at that point. And then it'll be long enough for me to do a y equals mx plus b calculation with. Right? So for that one there, for time 2 seconds, okay, I would draw a tangent line that looks, well, that's not very good, but I can adjust it. Okay, that's probably a little bit too steep. Maybe something more like that. Okay, so now I've got a line that's got a y-intercept. Okay, and I've got I've got a grid intersection right there. Okay, right at time 2 seconds that I can use. Okay, and know my y and x values. So I would say, okay, y is going to be 10, x is going to be 2, b is going to be 5. Everybody follow me there? Okay, and then I'm going to go m equals y minus b over x. Okay, and we'll have our 10 minus 5 over 2. Okay, so it should be 2.5. Okay, I have 3 meters per second there because probably the last time I did that, my best fit line or my tangent line was a little steeper. Okay, so this would be an approximate. In fact, all of these answers would be approximate values because you're going to draw the tangent a little bit differently than I did. Okay, that's showing that even I'm not drawing it all that consistently. Okay, which is, again, a reason why you probably wouldn't get a question like this on a test. There would be such a wide range of answers, okay, for it that it would be difficult to mark. Okay, but that's how you do it. We have to remember that on a position versus time graph, we can get velocity from the slope of the line because that's total displacement over total time. Okay, so what usually comes up with a question like this when we're trying to find displacement off of a velocity versus time graph is people remember that we got to use average velocity times time, which means calculating the areas, okay, of our shapes, but they often forget that below here has to be included. Oop, that's not very straight at all. Okay, goes to there. Okay, so this whole rectangle has to be included here, not just the upper part. All right, so I've got these shapes here, right? Because I have to include that at some point I was going faster than 20 meters per second. If I only do this part, then I'm not reflecting what I would have done before I started to accelerate, which is the lower part. Does that make sense? Okay, I mean, you can distribute this however you want. You could probably make it just one big rectangle all the way across the bottom here. Okay, and that would probably be the most effective way to calculate that. Just do that rectangle in there. Okay, this rectangle, this triangle, and this triangle. Add them all up. Right? So it's always the total area between the line and the x-axis. That way it includes when it's upside down and it's below.